Okay.
Oh, let's start. So yeah, welcome to this week's Tyra Talks, and this week it's it's my pleasure to have Dr. Pinghan Chu from Los Alamos National Laboratory to talk about search for new physics with atoms. So let me briefly introduce Dr. Chu. He's the scientist at the MPA-Q group at the Los Alamos Laboratory now. He received his PhD in physics from the University of Illinois at Urbana-Champaign in 2011, where he worked on the Dressed spin technique in the neutron electric dipole moment experiment with Professor Zhenjie Pen. And after earning his degree, he joined Professor Haiyan Gao's group at Duke University to research exotic spin-dependent interaction. In 2014, he joined Dr. Steve Elliott's group at Los Alamos lab, where he studied neutrino-less double beta decay in 76 germanium using high-purity germanium detectors. This would earn him the Small Team Distinguished Performance Awards in 2018, and he was converted to a staff scientist in LANL in 2019. In 2021, he received the LDRD Early Career Awards from the National Lab. Dr. Chu has also been involved in other projects in the National Lab, including the research on neutrino physics and dark matter. Before I turn the stage to Dr. Chu, let's unmute ourselves and give a round of applause to Dr. Chu. Ready? Go.
Okay. So may I start?
Yes, please. Thank you.
Okay. Yeah, thanks for the introduction. Yeah, so today I'll talk about my research about the atomic physics. So MPA-Q here is quantum. So here I will use some so-called quantum sensor in this talk. Okay, so in this talk, at beginning, I'll briefly what kind of new physics I'm looking for here, mainly about the matter-antimatter asymmetry and dark matter. And I'll describe one of the most powerful candidates, so-called axion, here. And I'll describe two experimental approaches in this talk. One is spin-dependent actions. Another is, can someone admit Zhen Yunting? Okay, good.
Yes, I did.
And the LC circuit. Okay. Okay, so here's a brief history of the universe. If you don't know, universe starts at a so-called Big Bang. So it starts from a singularity point. And then after that, it starts to become very big, so-called inflation. And then this process will generate everything we can observe today, like the particle, like the atoms we can see. Okay. And at beginning, we have the pair production and annihilation. That means the energy can become particle and antiparticle, and antiparticle can become particle and antiparticle can annihilate and become energy. And because now the temperature is very hot, so these two processes, they are in a thermal equilibrium. However, so you know, when the universe becomes big, the temperature becomes cold. So something happens, something we don't quite understand why, but there are more matter than antimatter. So the ratio is about 10 to minus 10. So it is just very small amount. But this small amount create everything we can observe today, including all the atom and all stars we have here. So this is so-called matter-antimatter asymmetry. Okay, so the background, so here the matter-antimatter asymmetry is proportional to background asymmetry of the universe, and the ratio is about 10 to minus 10. This was determined by the cosmic microwave background radiation. So you can see if you see some kind of scientific news, you'll see this kind of plot. This just show the population deviation of our universe. And in order to explain this matter-antimatter asymmetry, Sakharov, who proposed three conditions. The first one is departure from the thermal equilibrium. This thing is quite easy to understand when the universe became cold. So you don't have the so the pair production and annihilation won't be equal. The second one is the baryon number non-conservation. So you need some process so you can have more baryon than the lepton. So this one of this process physics are looking for is the proton decay. So this process, you'll have the proton in the initial state, but in the end, you won't have the baryon. Proton is the one kind of baryon. You only have lepton and boson. The third condition here is the charge parity variation. Charge parity is the symmetry between the matter and antimatter. So here you have more matter than antimatter. In most conditions, matter and antimatter, they behave similarly. But this, in some special scenario, they are different. For example, here, CP variation was first observed in K-on B system and the B meson system. That means the B, this B quark and B bar quark, they are not the same. So we have K long and K short, these two mesons, and their behavior are different. And these phenomena can be well explained by Kobayashi-Maskawa mechanism in the standard model. And this explain the quark mass eigenstate and quark flavor eigenstate are not the same. You can use this CK matrix here to rotate, to convert from the one eigenstate to the other eigenstate. And there's an imaginary part in this CK matrix. That's why the matter and antimatter are not the same. However, the baryon, based on this Kobayashi-Maskawa mechanism, we only can explain baryon and photon ratio is about 10 to minus 18. So you can see the observation of baryon symmetry and the theoretical prediction here are very different. So in order to explain this, we need more sources for CP variation. One of them is in the electric dipole moment. So electric dipole moment is the first moment of charge distribution. So EDN is a vector by definition, okay? But as we know, in a fundamental particle, the only intrinsic direction is the spin, and spin is an axial vector. So you can imagine when you apply a parity operator, the parity operator is the symmetry between here and the behavior in the mirror. So you can imagine what have the interaction. You can observe if this interaction in the mirror will act differently than here. So if we apply the parity operator here, you can see the charge distribution is reversed, but not the spin direction. Okay, so this implies an EDN violates parity operator, a parity symmetry. Similarly, if you apply a time reversal operator, then here the charge distribution is the same, but the spin is reversed. So EDN also violates time reversal symmetry. And if you know CPT is the good symmetry because of the Lorentz variation invariance, then T variation implies CP variation. So a non-zero EDN implied a new source for the CP variation. Okay, that's the basic idea about EDN. Okay, here I want to go to another stuff, a so-called strong CP problem. So in QCD Lagrangian, QCD is the quantum chromodynamic, which describes the quark interaction. It also allows a CP vibrating turn, so-called the strong CP turn. It's proportional to the Coulomb field strength tensor and strong coupling constant and the fundamental parameter, so-called theta here. And theta is a value between 0 and 2 pi. And this value is related to the neutron electric dipole moment. And our current limit is 10 to minus 26 E dot Cn. Cn is the centrometer. And we can use this equation here. The neutron EDN is proportional 10 to minus 16 times theta bar. And theta bar is the theta minus the quark mass matrix contribution for the neutron EDN. And we have the neutron EDN upper limit, and we have this equation. So theta bar's upper limit is roughly 10 to minus 10. This is unnaturally small. This means the strong CP contribution can be canceled out by the quark mass matrix contribution. And there's no good explanation why these two parameters, these two or physics constant, can cancel out with each other. So this is we so-called unnatural. Okay, so in order to explain this strong CP problem, some physics, Pache and Quinn, they propose to use a dynamic variable to remove any contribution to the neutron EDN. This is so-called axion. So axion is a field which can couple to gluon, and it has the same interaction as the strong CP term. So it also proportional to the gluon field tensor, and it has proportional some other parameter, the A and the FA here. They are just show the field amplitude of the axion. Okay, and this field is a dynamic field. It's generated from the Goldstone boson with a spontaneous symmetry breaking. So this idea is kind of tricky. I try my best to explain this, but we can discuss this more later. So in the beginning of the universe, when the universe is hot, so the potential is symmetric. And then when the potential, when the universe became cold, this potential kind of change. So you have this asymmetric form. So at the central point, it's not a minima at all. So we know the nature like to go to the minima potential. So you won't be at center to keep the symmetry. You will break to a certain direction. And this process will generate the Goldstone boson. And this Goldstone boson is our axion. And its mass is proportional to the energy scale Fa here. And axion is massive, so main axion can be also used to explain another puzzle in physics, the dark matter. And we'll talk about that next. So axion here is similar to Higgs field. So we know Higgs field is a boson which can couple to everything and generate a mass turn. So it's a kind of uniform field in our universe. So since we already observed Higgs, so it's not too crazy to have another field in our universe, uniform field in our universe. And axion can couple to different different particles like quark, gluon, photon, leptons. So there are many methods which can be used to detect axion. And we'll talk about that later. Okay. So let's come back here. In this picture of the universe, there's no dark matter. But dark matter, in fact, exists. It's about 27% of the mass and energy in the universe. and observation of dark matter all from some kind of gravitational effects. So we can see the rotation curve of the galaxy. So if you see the galaxy's rotation speed, you simply you can use the Newtonian law to estimate how fast it can rotate. But Bertha Rubin, she discovered the rotation speed become faster and faster at outer ring, which is not which cannot predict by the observed mass in the galaxy. So this implies there's something more in the galaxy to generate such fast rotation. So this is the first evidence about or clue about the dark matter. The second one is the gravitational lensing. Now we have observed so many gravitational lensing in our sky, in our universe. So as we know, the mass can attract the light and change the light traveling direction. So this effect can change the light from the far away galaxy and form a ring around this galaxy. So this is so-called the gravitational lensing because the effect is just like a lens there, which can bend the light. The less evident here is the cosmic microwave background radiation. Again, we need a dark matter to explain our data. And with this result, we can estimate dark matter is about 27% of mass and energy in the universe. So I forgot to mention that. So the dark matter density is about 1 proton mass per centimeter cube. Okay, now for a long time, people search for the so-called weakly interacting massive particles, so-called WIMP, and they make so many kind of experiments, but so far we still don't discover the dark matter. Okay, so and WIMP usually the mass. Usually people are looking for the WIMP mass from the 1 GeV to 100 GeV. And now we are already close to the neutrino background. Neutrino can also have a similar interaction as the WIMP. So if we improve our sensitivity, then we will discover the neutrino. We cannot separate the effects from dark matter or neutrino. That's why physics are considering other mass scale. For example, the light mass scale for the dark matter. And one of them is the axion. And as we know, axion here, its mass is inversely proportional to the energy scale. So using the axion, we can also search for like grand unification theory or Planck scale, which cannot be explored by current accelerator collider technology. So axion is a promising candidate for dark matter and for many reasons. So in this talk, I'll spend some time to explain how do I search for axions. So there are many ways to search for axions, like the horoscope. Here, axion can convert to photon in the B field. I'll talk about this when I describe my experiment LC circuit. Another is one helioscopes. So here we know axion can generate from the sun, and then we can use the Planck scattering or some noble gas to detect the axion. Axion can be converted back to the photon, and then we can see that in our detectors. Okay, another one is we know photon can also be converted to the axion. So here we use laser, we shoot laser through a very strong magnetic field, And then we have a wall behind to stop the laser. But the axion can pass through the wall. So if we can see the signal behind the wall, then this probably will be the axion signal. Another one is the short range interaction, which I'll describe in my talk. Okay, so I'll talk about these two approaches in my the talk. One is the spin-dependent interaction. Its mass range is about 10 to minus 6 eV to 10 eV. And the LC circuit is from 10 to minus 11 eV to 10 to minus 7 eV. Okay, let's talk about the spin-dependent equations. Okay, so after the axion was proposed, people start to think about maybe there's some other interaction which can be used to search for axion. So one of them is the Moody and Will check. They consider the interaction between the polar and apolar particles. So this kind of dipole and monopole interaction can be mediated by massive spin zero boson, which could be an axion. Okay, so here are two interactions, their potential form. So this potential 9 plus 10 is proportional to the spin dot r. R is the direction between two particles. One of the particle is polar, another is unpolar. Potential 3 is the interaction between the polar and polar or dipole-dipole interaction. So you can see the potential here. Okay. So later, other people were inspired by the Moody and Will check. So they consider another scenario by including the velocity between these two particles. So they extend the concept to have like one spin and velocity interaction, or two spin interaction, or two spins and velocity interactions. So you can see some of them value t, some value t. If you apply a t operator or t by operator here, you'll see it's just similar to the electric dipole moment. So there could be a new source for t variation or p variation. So it's a non-possible source for the spin variation as well. Okay, let's summarize the spin interaction here. So this new interaction can be mediated by very light, weakly coupled boson like axion. And these massive particles can be dark matter candidate. And some of them violate P and T, so they can be also new sources for the CP variation. And here, the most important for this new interaction is very similar to a magnetic field. Okay, so this is a potential for plus 5. So it's proportional to the spin dot V plus R. So you can simplify as the interaction as the spin dot A, which is very similar to a spin in a magnetic field. That's why we can detect this interaction by very sensitive magnetometers. So here is a summary plot for the potential 9. So people, you can see the x-axis is the lambda. Lambda is the length scale, or you can is related to the mass scale of this new interaction. And the y-axis is the interaction coefficient, coupling coefficient. That means just how the amplitude of this interaction. So you can see there are many different experiments about these interactions, and they use different technologies like the torsion pendulum, squid, or diamond magnetometers. And now we are very close to astrophysical limit. So I will talk about some of our experiments using different technology. So the first one is the atomic magnetometer. The idea is based on the laser and alkaline metal like rubidium, potassium, or cesium vapor cells. And we can use upon laser beam to polarize atomic spins. So here the rubidium atom energy level. So a circular light can excite the ground state to the excited state. However, when it decays to the ground state, it equally decays to spin states. And circular light can only excite a certain spin state. So using this process, we can make all spins, we can make all atoms at a certain spin states. So the spin is polarized here. And then we can have another probe beam, which is perpendicular to the rubidium spins. And then once the spins are tilted because an external magnetic field, then this probe beam polarization will be different because of Faraday effect. So Faraday effect is the spin can change the polarization direction of the laser light. And then we can have detector to observe how much the laser light polarization changes. And using this method, we can detect very small magnetic field. And atomic magnetometer is the most sensitive cryogen-free magnetic field sensors, which can reach a femtotesla level. It means we don't need a cooling system like squid. We can use this in the room temperature. And we also can reach a similar sensitivity. So how do we use atomic magnetometer to detect spin-dependent interactions? So here is our proposal in 2018, in 2016. So we put some mass on polar mass or polar mass nearby to the rubidium cell. And a particle between the rubidium atom and a particle in the mass can generate different kind of the spin-dependent interaction if we change or the moving pattern of this mass. So using this method, we can measure the spin-dependent interactions. And for the unpolarized mass, we use the BGO, which is a very dense crystal. For the polarized mass, here's an R&D we have. So according to this paper, there's a rare earth iron garnet. This kind of material, it can have the polarized spin, but no magnetic field at a certain critical temperature around 240 Kelvin. The idea was proposed by Josh Long at Indiana University. And so we plan to build a cooling system to lower the temperature of this iron garnet. So we still can have polar spin here, but the magnetic field induced by this mass can be very small. Okay, so here is the measurement method for potential 4+5 is proportional to spin dot velocity close R. So in order to get this interaction, we rotate our BGO mass in front of our rubidium cell. So you can calculate what kind of interaction, the interaction direction. So you'll see the potential 4+5, the field potential 4+5 will be along the vertical direction. Okay, here's our experimental setup. So we put our sensor in the mu metal shielding in order to reduce external magnetic field. And then we use a very long rod to support the mass. And then we we have a motor outside. We can rotate the mass to generate the effective field of potential 4 plus 5. And then we also can change the rotation direction. Here we can cancel out the systematic field from the impurity or external environment, but our effective field A plus 5, 4 plus 5 can also can change its direction when we rotation the mass change as well. Yeah. So here's our result. So our effective field is within 0, and our sensitivity is about 4 times 10 to minus 16 Tesla. So here's our result. So we can make a new limit around the centimeter region, where the mass of axion is about, the mass is about 10 to minus 3 eV. So the result was published to PIL in 2018. Then next, we also do the interaction 12 plus 13. This interaction is proportional to spin dot velocity. And then we move the mass nearby the vapor cell. And we also can improve the limit around the similar interaction range and the mass range. The result was published in 2016. Okay, now we have some new proposal. So one of our constraint is the distance between the mass and our Lupin cell. As you know, the Lupin cell is in some glass cell. So there's a wall thickness, which is about a few millimeter. And we also have some kind of thermal shielding, because in order to generate rubidium gas, you need to heat to around 120 Celsius. So it's a little hot. So you have a roughly 1 centimeter gap. That's why our sensitivity is around 1 centimeter here, this kind of range. But so here we propose to use the flash guide. Flash guide is some ferromagnetic material which can kind of deliver the magnetic field very near to the magnetic field and transfer this field to the vapor cell. So using this method, we can improve our distance. So we estimate our distance will be roughly 10 micron. Okay. So we'll come back to this idea next when we talk about diamond. Okay, another proposal we had is using the paramagnetic insulators. So this material have been used to measure the electric dipole moment. This material's name is GGG. So in the magnetic field, the spin can be polarized. And we can use a squid to measure this polarization. So here we propose we can we can move some mass, VGO mass, near to the this material GGG. If there's this new interaction, this spin direction will polarize spin, and this can be measured by squid. Okay, let's talk about diamond magnetometer. Diamond is a kind of so-called quantum sensors here, because it can measure very small, very short distance interaction, magnetic field in short distance. It can even measure a single atom spins. So the basic idea is you put the nitrogen vacancy dope in the diamond. And because the diamond is solid, you can move this doping, this NV center very near to the surface. Okay. So here there is about, it can be around 10 nanometer close to the surface. And then we can use spin echo to measure the phase shift due to the external magnetic field. So again, similarly, we can move some mass near to the NV center of diamond. And use this, we can measure the interaction within a very short distance. So Ron and his group published the first result with diamond in 2018. However, later they published several results with diamond and however, one of them in 2020, they claim they discovered a new interaction. They claim they discovered the potential for +5. So this potential is depends on the velocity. So you can see when they change the velocity of the mass, you can see the interaction also changes. And also it has a distance dependence. So here is our proposal. So I propose a new measurement with the Professor Acosta in University of New Mexico. Professor Acosta, he is an expert of NV diamond. So here is our proposal. We believe we can, using very high frequency and EMS, electrostatics combined drive, to move the mass. It can increase the speed about 3 order. And he also optimized the geometry. So eventually, I think we can improve the sensitivity up to 5 orders at the region of interest. So the black triangle is the region this Chinese group claimed to discover a new interaction, and blue dashed line are the sensitivity we claim we will have. Okay. And in the same paper, we also propose we can use the copper 13 nuclear spin as the polar mass. So we can consider the first electron spin, nuclear spin, velocity interaction. Of course, in order to polarize copper 13, we need to do the experiment in a cryogenic environment. Okay, so here is our sensitivity plot. Okay, so polar helium-3, this is an experiment I did when I was at Duke. So here we use polar helium-3. We can use the so-called spin exchange optical pumping. Here we can polarize the rubidium cell, as we just described in atomic magnetometer. And the rubidium atom can collide with helium-3 and transfer the spin from rubidium to helium-3. So using this method, we can efficiently polarize helium-3 nuclear spins. And here is our device. So our cell, helium-3 cell, is in the center of the Hammers coil. And then we have a mass. We can move the mass near to the helium-3 cell. So here's our result signal. So you can see here we use the free induction decay. So we apply a small field, I field, which can rotate the spin to 90 degrees, and then you start to precess along the magnetic field, and then the precession will decay. Okay, so this black signal is our this free induction decay signal. So we just measure this signal when we have mass and when we don't have mass, and subtract it too, and then we get our result and make a new up limit here in the red dash curve in this plot. So the result also published. Let me see. published in 2013. Okay, so recently there's another promising experiment so-called axion-like. So as we know, when you know the polar helium-3 spin can present in a magnetic field, and if we apply a RF field which at resonance frequency, it can kind of tilt the polar helium-3 spin. Okay, it can rotate the helium-3 spin at resonance frequency. So here, what we want is we use this mass to mimic this RF field. So we need to rotate the mass very fast. So its effective field is at the resonance frequency as the this helium-3 spin. Okay, so they proposed this idea in 2014, and they plan to use squid in around the helium-3. However, I think we also propose a similar idea. Not only potential 9+10, we can also consider other interactions. And we also can use our device similar to our Duke experiment. So we don't need to do the experiment in a low temperature environment. We can do it in a room temperature environment. So here's our sensitivity plot. So even though we are not as sensitive as the axion-like experiment, but I think we still can make a reasonable improvement by using this resonance method. So after we propose this idea, I think another Chinese group, they use polar xenon and using this resonance frequency and significantly improve the sensitivity of the interaction. So you can see the result, the green curve here. Okay, let's talk about my other experiment, LC circuit. So here, axion can couple with photons. So its Lagrangian is proportional to E dot B. E is electric field and B is magnetic field. And GA gamma gamma is axion photon coupling. Okay. So this effect can modify the Maxwell equation. So in this Stickvitz paper in 1983, he make this kind of modified Maxwell equation. Okay, I should do this. Okay, so the current limit, one of the most promising axion experiments, ADMX. They use the cavity and search the axion around 10 to minus 16. So they already approach some kind of QC axion sensitivity region, the yellow band here. The LC circuit is another new proposal. Originally, it was proposed by Stickvitz and his colleagues. So here, we have a static magnetic field and no electric field. So we can kind of simplify this equation, and we will see some oscillating field B8 here, which is related to the axion field. Okay, so we can measure this oscillating current from this oscillating axion field by LC circuit. So here is a proposal. So we have the holding the B0 static field from the solenoid, and this static field can couple with axion and generate this oscillating field BA, and then we can put some LC circuit, and this BA can induce some oscillating current in the circuit, in the coil, and then the coil, we can measure the output signal using a very sensitive atomic magnetometer. So that's the basic idea here, and we don't In original Stiglitz proposal, he proposed to use squid. Now here we just propose just use room temperature, just do the experiment in the room temperature environment. So here our sensitivity estimation. So the top plot is to show you our atomic magnetometer sensitivity is about 2 femtotesla per square hertz. And the dominant noise is Johnson noise and atomic magnetometer noise. And Johnson noise basically the thermal noise is it dropped for high frequency. So at a certain point, we'll reach the Johnson noise will become comparable to the atomic noise. So this is the frequency range we like to use the LC circuit to search for. Okay. So here's our sensitivity plot. So the current limit is the test limit. And our blue dash one is our room temperature proposal. And Stiglitz squid proposal is the green dash curve here. And yeah, so I think this proposal was funded through the LDRD of LANL. Okay, summary. So I have introduced several new methods result searching for new ways using the atomic magnetometers, like spin-dependent interaction, LC circuit, and there are many other new proposals ongoing. Okay, thank you.
Thank you for Dr. Chu's talk. The floor will be open for English questions right now. Feel free to unmute yourself and ask questions. If we don't have English questions from the audience, I'll stop the recording now and we can move on to the discussion. So thank you for watching.